All right, so in this unit, we will be diving into chemical naming, how to name and write formulas for basically every chemical you'll come across. And since this unit is very long, I will be splitting this up into two videos. So there will be a part two coming in a week and a half, maybe 2 weeks. Anyway, so we have to go through some review type stuff. First up, ions. You should already know that a cation is the positive one and the anion is the negative one, and that in ionic bonding, the attraction between them is what holds them together. You should also know almost every single atom on the periodic table's charge just by looking at it. This was the VIP from our last unit, and you should hopefully be familiar with it. Again though, group 1 atoms have a +1 charge, group 2 atoms have a +2 charge, group 13 has a +3 charge, 14 doesn't usually form ions, but it could be +4 or -4 depending on the situation. Group 15 is charged -3, 16 is charged -2, group 17 is charged -1, and group 18 is unreactive, and they do not form bonds or ions. In the transition metals, most of them have more than one oxidation state, meaning they can have different charges depending on what they're paired with. But some of them, like silver and zinc, only exist as one oxidation state. Zinc will always be a +2, and silver will always be a +1. This was also on the VIP, by the way. Okay, so next we're going to go through some step-by-step instructions on how to name binary ionic compounds. But first we need to define what that means. Binary means two, ionic means ions, right? So that is to say that one of them are positive and the other is negative. Nothing too crazy yet. So the first thing you need to know is that the cation always comes before the anion. Whether you're writing a formula or a name, the cation will always be the first one. Then, the name of the cation is actually just the name of the element. This means that when you see Na+, we just call it sodium, even though it's the sodium ion. Next, the second word is the anion, except we have to change the ending to let everyone know it's the anion. So we change the name to have IDE at the end. Last step is just to put them together, so the example of NaCl is called sodium chloride. We change the ending of chlorine to IDE to get chloride. Now it does get slightly more complicated, but that's the gist of it. So let's go through a few examples. The first example is CaCl2. We name the Ca2+ ion as calcium, and we name the Cl-1 chlorine as chloride. We put those together and we get calcium chloride. Easy. This time we need to go the opposite direction. Let's say you had a name like aluminum chloride. What you're going to do here is write the formulas for both the cation and the anion. You must include charges. Remember, the charges can be found on that VIP 10. If the charges are already balanced, you don't need to do anything, just rewrite the formula without the charges. Like, writing the charges is how we show our work in getting what the formula is going to be, but it's not actually a part of the formula. So these are unbalanced. The 3+ and the 1- do not even out. Our goal is to get the overall charge to be 0, or to say it in a different way, we want the plus side to equal the minus side. So the question becomes, how many chlorines do we need in order to balance out that +3 charge from aluminum? Obviously, the answer is that we need 3 of them. So this would be a good time to mention that the charge of a singular ion goes at the top as a superscript, and the subscripts at the bottom represent how many of that ion you need. So if we need 3 chlorides to balance out the aluminum, that means we put a 3 down here, and it becomes AlCl3. Slightly more challenging example here, aluminum sulfide. Again, we are going to write out the chemical symbols and the charges. They are not balanced already, so we need to balance them, but this will be tricky. We need to get them to be the same, but that's not easy if they're a 2 and a 3. So what we actually need is the least common multiple of 2 and 3, which is 6. If we can get them both to be 6, then they'll even out, right? Well, how do we get the aluminum, which has a charge of +3, to be 6? Or like, how many aluminums would we need? 2. And how many sulfides would we need to get -6? If each one of them is a -2, well, we'd need 3, right? So then the balanced formula becomes Al2S3. There is a shortcut that I don't really like. It's the crisscross method. Basically, if the charges are unbalanced, you crisscross the charges to become the opposite one's subscript. But in my opinion, that will mess you up more than it will help. There's also this little note down here that will be very important later on. Use parentheses if you need more than one polyatomic ion, which is something we'll talk about in another minute. There are just a couple more types of namings we need to go over. Whenever we see one of those transition metals, we have to tell which ion they formed. We have to tell the charge of the transition metal, and we do that with Roman numerals. So we have this example, PbCl2. The Pb is in the transition metal ? zone, but we can figure out its charge based on what it's bonded with. The Cl we know has a -1 charge, and since we needed 2 of them, the formula tells us that, we can figure out that the lead must have been a +2. So when we write out the name, we will use Roman numerals to represent that +2 charge. So the name becomes lead-2 chloride. We can also go the opposite direction here. If you're given the name iron-3 iodide, you will follow the same steps as before, writing out both chemical symbols with the charges of both. The I is -1 from VIP10, and even though the Fe is in the transition metal ? zone, we know what the charge is this time because it tells us in the name, iron-3. The Roman numeral 3 there is the charge of the iron. So with both charges, there's just one more thing to do. Either crisscross or ask yourself, how many iodides do you need to balance out that +3 from iron? Yeah, 3. So the formula becomes FeI3. Okay, there's only one more thing we need to know about naming ionic compounds before we can name absolutely anything we come across. It's this thing called polyatomic ions, which are basically a collection of atoms that when they come together are so stable, they actually can go through an entire reaction as a clump all together without breaking apart. So they are kind of treated as if they're only one ion, even though it has multiple atoms to it. I know, definitions never make sense until you see them used in practice. As it says, there's no great way to learn these other than just memorizing them, which is what I had to do. But of course, I gave them to you on a VIP, so you don't have to memorize them. You're welcome. Now these look a little weird, but you'll get used to them over the next week. Just make sure you know the difference between a subscript and a superscript, because these will have both. Oh, and when the charge doesn't have a number like the first one, ammonium, it's a 1, so its charge is +1. Okay, so here's an example that both the cation and the anion are polyatomic ions. Ammonium sulfate. We'll need to go to VIP 11 and find both of those names. Ammonium is NH4+, and sulfate is SO4 2-. Make sure you also notice the difference between sulfate and sulfite. Okay, so now we've got those two written down. We can see that they're not balanced, right? So the same question as before, how many ammoniums do we need to balance out that -2 charge from sulfate? 2. Now that little note at the bottom comes into play. When we need multiples of a polyatomic ion, we have to use parentheses around it, so it becomes NH4 2SO4. You will absolutely be required to do this very soon, by the way. All right, this example is named magnesium carbonate. So we write Mg and its charge of 2+. We find carbonate on VIP 11, which is CO3 2-. This is a strange example. Look, the charges are the same. They already balance out. This means we don't need any subscripts on either ion, and the formula is just MgCO3. Just a couple more examples here. We're going to find a formula for zinc hydroxide. Zinc on VIP 10 is always a positive 2 charge, even though it's a transition metal. It's one of the only ones that has a set oxidation state. You'll find hydroxide on the VIP 11, which is OH 1-. So again, zinc and hydroxide do not even out. So you would ask yourself how many hydroxides you need to balance out the positive 2 charge from zinc. And remember, when we need multiples of any polyatomic ion, we need to use parentheses. So the formula becomes ZnOH2. Another similar example here with barium nitrate. So we write out Ba and its charge is 2+. We find nitrate on the VIP 11. We write that as NO3 1-. So you can probably see the pattern by now, right? We're going to need 2 nitrates to balance out the barium charge. And again, we're going to need parentheses around nitrate. So that gives us BaNO3 2. Last example here is aluminum phosphate. We find the aluminum on VIP 10 and the phosphate on VIP 11. Al has a 3+ charge. Phosphate has a 3- charge. This means they are already balanced, and the formula is simply AlPO4. Our last topic here on naming is naming covalent molecules. Binary again means 2, and these are not ionic, and do not involve any metals or ions. The first 2 rules are the same as ionic compounds. The first one says to name the element that comes first, same as before. The ending of the second element is again changed to IDE. The one big difference is that you will need to use prefixes to tell us how many there are of each atom. Here are all the prefixes, and these are also on VIP 11, so you don't have to memorize them. Again, the numbers on the right are how many each atom you have, and the prefix is what we write before the name of the element. And here are some examples. P2O5, we write the phosphorus, and we change the oxygen to oxide. And then we need to say how many phosphoruses there are. And since there is 2, we use di, and we put that in front of phosphorus. Same thing with the oxygen. The prefix for 5 is penta, so we put penta before oxide. So the whole name is diphosphorus pentoxide. Obviously, you've seen CO2, and you know it's called carbon dioxide. This is because there are 2 oxygens, and the prefix for 2 is di. Carbon monoxide, same thing, except mono is the prefix for 1. You may have seen from 2 slides ago that it said you do not need mono for the first element in naming. Anyway, last example here, how many nitrogens, how many oxygens? N2O is named dinitrogen monoxide because again, the prefix for 2 is di and the prefix for 1 is mono. Okay, like I said, I'm breaking this unit into 2 videos because of how long the notes are here and with how much practice we get with naming over the next week or 2. I just think it'll work out best if we cut it there. Anyway, look forward to those coming to Schoology over the next week. And of course, let me know if any of the naming is causing you problems. And as always, thanks for watching.